Hello, everybody. This is Glenn with No Dead Puppies. And today we're going to look at the chain rule in our calculus book for my class. This is section 3.6, or is it 3.7? Well, it's one or the other, but we're talking about the chain rule here. And the objective here is to look at finding the derivative of composite functions. Now, if you recall from pre-calculus, a composite function is simply put, a function that's within another function. So, for example, f of x equals 2x plus 5 squared. So we can see that there's an outer function, which is the squaring function. The inner function is 2x plus 5. So anytime we have like these sort of nested expressions, we have a composite function. Now, how do we find the derivative of a composite function? Well, up to this point, a composite function, say, for example, like 2x plus 5 squared, we could simply expand, multiplying 2x plus 5 by itself, getting 4x squared plus 20x plus 25, and then differentiating term by term to get the derivative, which in this case would be 8x plus 20. Now, of course, things get a little bit problematic if we wanted to, say, find the derivative of a function, say, like 2x plus 5 raised to the 10th power. You could expand that, but you'd probably spend more time expanding it all the way than actually differentiating it. Okay. And then, of course, what about other types of composition of functions that we really don't know how to handle? Like, for instance, say the sine cubed of x minus 3. We know how to find the sine, the derivative of the sine function, but not cubing the sine function. And also, in addition, even without the cube, if you just had the sine of x minus 3, that's a composition. We don't have anything for that, although we know basic derivatives of trig functions. So the chain rule is a formula that we use to differentiate compositions of functions, in particular those that we couldn't evaluate just by expanding and simplifying. So now let's take a look at the chain rule itself. All right, so here we have the chain rule. So on the left side, we have the derivative with respect to x of f of g of x. Now, here is the composite function, because remember, as I said, you have a composite function has an outer function and an inner function. So in this case, f is the outer function, g is the inner function. The derivative with respect to x of f of g of x is equal to f prime of g of x times g prime of x. Now, another way of using it with the different dy dx notation would be something like this: dy dx equals dy du times du dx, where u is sort of that transition function. Now, what this all means basically, and this isn't the most precise way of putting it, but it's a way that I hope that you can understand. It's basically stating that the derivative of f of g of x is the derivative of the outer function multiplied by the derivative of the inner function. So you're going to take the derivative of the outer function with respect to the inner function, and then multiply that by the derivative of the inner function. Now you'll see that in play as we do some examples. So I have 4 examples here that we're going to take a look at, which hopefully should give you a good idea of how we use the chain rule and prepare you to do your own practice. All right, so let's say, for example, we want to find the derivative, dy dx, for the function y equals x squared plus 3 raised to the 4th power. Now, as we can see in this function, we have a composite. The outer function, we have the inner function and the outer function. So our inner function is simply x squared plus 3. The outer function, I'll call that u. I'll use u to represent everything that's inside, is basically u to the fourth power, because you have the fourth power, that's the outer function. So if we differentiate this, dy dx, so it's going to be first the derivative of the outer function. Well, if you differentiate the outer function, u to the fourth, its derivative would be 4u to the third. Now here, since our u is actually x squared plus 3, the outer function derivative would be 4 times x squared plus 3 raised to the third power. So now that's the derivative of the outer function. And then we multiply that by the derivative of the inner function. The derivative of x squared plus 3 is equal to 2x. So that'll be times 2x. And then we can simplify this. We can multiply 4 and 2x together. So the derivative here would be 8x times x squared plus 3 to the third power. Now, this is something that you could actually confirm by sort of by brute force. If you wanted to and you had the spare time, you could fully expand x squared plus 3 to the fourth power and then differentiate term by term, and then compare that to what we have for the derivative here, expanding it and looking and comparing it term by term. All right, so this is going to be our derivative for this function. Let's take another look at another example. This example, we want to find dy dx for y equals -8 over 3x minus 4 squared. Now, if you look at this one, you might consider, oh, this is a quotient because we have a fraction, and so we might have to use the quotient rule here. And whereas that is feasible and you could do that, it's really not necessary. Since the numerator is a constant, we could just as easily write this as -8 times 3x minus 4 raised to the negative second power. All right, so now let's apply the chain rule here. So in this case, the outer function is going to be u to the negative second power. If we want to include the -8, we could. It's a constant, so let's do that. And our inner function is 3x minus 4. So when we apply the chain rule, we take the derivative of the outer function. So now for 8u to the negative second, its derivative would be positive 16u to the negative third. Now, since our u is 3x minus 4, this comes out to 16 times 3x minus 4 raised to the negative third power. And then we multiply that. That's the derivative of the outer function. We then multiply that by the derivative of the inner function. Derivative of 3x minus 4 is simply 3. So it'll be equal to 3. And then we can clean this up. We can multiply the 16 and 3 together. That gives us 48. And if we want to be neat about it, we can put 3x minus 4 to the negative third power, bring that down to the denominator, write that as 3x minus 4 cubed. Now, the important thing about using the chain rule is being able to correctly identify the outer functions and the inner functions when we're working with these problems. All right, so now let's look at a couple more problems. And let's throw in some trigonometric problems here just for the fun of it. So let's say we have the function f of x equals the sine of e to the x plus x squared. All right, so once again, let's identify the outer functions and the inner function. Now, the outer function we can clearly see is going to be the sine function. So here we're looking at the sine of the inner function, the quantity u. And the inner function is e to the x plus x squared. So when we differentiate this, f prime of x, we take the derivative of the outer function. Derivative of sine is cosine. So we'll start by taking the cosine of the inner function, e to the x plus x squared, times, and then we multiply that by the derivative of the inner function. Derivative of e to the x plus x squared is going to be e to the x plus 2x. So we multiply that by e to the x plus 2x. All right, so if we want to maybe look at exchange the terms just to avoid confusion, this would be e to the x plus 2x times the cosine of e to the x plus x squared. All right, so I hope this is making sense for you. Okay, as you can see, there's kind of a we're seeing the same pattern emerge over and over again. You're taking the derivative of the outside, multiplied by the derivative of the inside. Now, let's get to some more challenging problems. One of the real challenges of the chain rule is, of course, remembering the rule itself. But then when we start to mix it in with other types of properties and rules, like the product and the quotient rule, we need to be extra careful because we don't want to apply the rules out of order. All right, so let's say, for example, we have the function y equals e to the x over x plus 1 raised to the 8th power. All right, so now we clearly see a composition here. All right, so we have the outer function, okay, which is this quantity raised to the 8th power. And then we have the inner function. The inner function here is e to the x over x plus 1. Now, note that the inner function is a quotient. So when we get to the point where we differentiate that, we're going to have to apply the quotient rule for that problem. So now let's find the derivative. So we have y prime. So now the outer function, derivative of u to the 8th, is 8 times u to the 7th power. So this will be 8 times this quantity, e to the x over x plus 1 raised to the 7th power. And then we multiply that by the derivative of the inner function. Now, the inner function is a quotient, so we have to apply the quotient rule. So now remember the quotient rule. If we have the derivative of a quotient, that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom function squared. So if we apply that here, you've got the bottom function, which is x plus 1, times the derivative of the top, the derivative of e to the x is e to the x, minus the top function, e to the x, times the derivative of the denominator, x plus 1. Derivative of x plus 1 is just 1. And then that's going to be all over the denominator, x plus 1 squared. All right, so now here, of course, as you know, with the quotient rule, there's oftentimes a little bit of cleanup that we have to do. But we've applied the chain rule correctly up to this point. All right, so applying the chain rule, this is what we'll have. Now we just have to clean things up. So we can clean things up in the numerator. So distributing the e to the x here, this is going to be x times e to the x plus e to the x minus e to the x over x plus 1 squared. So the e to the x terms will cancel out. So we can then write this as 8 times e to the x over x plus 1 to the 7th power times x e to the x over x plus 1 squared. Now, in some instances, it might be sufficient to leave it like this, although we could do a little bit more simplification here just to write it as one fraction, right? And if we do that here, this will give us 8 e to the 7x time, I'm just raising it to the 7th power, over x plus 1 to the 7th power times x e to the x over x plus 1 squared to get a result of 8x e to the 8x power over x plus 1 to the 9th power. Now, just a side note, depending on the preference of your instructor, or if this is homework that you're doing online, it may be sufficient to leave it as we did at this point here, all right? But you might notice that oftentimes, if you're comparing your answers or if you're looking at your answers in the back of a textbook, they may take the simplification a couple steps farther, all right? In which case, you'd have the result that we have here. All right, but the overall notion here is that you notice how we had to use a combination of the chain rule and the quotient rule in order to differentiate this. So you want to pay close attention to your problems to make sure that you know all the different rules that you may have to employ. And then secondly, making sure that you do them in the correct order. All right, so we're going to do one last example. And this is going to be an instance where we have a multiply nested composite function. As we said before, that a composite function is a function inside of a function. But now what if we have a function in a function in a function? So it's sort of a triple composite function. So let's say we have something like this. F of x equals tangent squared of 3x to the fourth plus x squared. All right, so now when we look at this function, you might think to yourself, oh, this isn't really a composite because you have tangent squared on the outside and you have the 3x to the fourth plus x squared on the inside. However, tangent squared basically means you're taking the tangent of the expression 3x to the fourth plus x squared, and you're squaring that. In other words, it would be more appropriate for us to write it this way. All right, and so now here you can clearly see the multiple nesting here because you've got three functions at play here. You've got your outermost function, okay, which is sort of u squared, and then you've got the middle function, which is your tangent function. I'll call it w, and then your inner function, which is the 3x to the fourth plus x squared. All right, so now when you take the composite, how do we do this? Well, remember that the derivative of a simply composite function is just the derivative of the outer function times the derivative of the inner function. So here, we just basically continue the process because if the inner function is a composite, then we just use the chain rule a second time, taking the derivative of that inner function and then multiplying that by the derivative of the function that's inside of that. So let's see this work out. So now that our outer function is u squared. So derivative of u squared is going to be 2u, all right? So f prime of x. So we'll deal with the outer function first, so that's going to be 2 times the tangent of 3x to the fourth plus x squared. Now that's just the outer function. Then we multiply that by the derivative of what's inside. So what's inside this? The tangent function. Now what's the derivative of tangent? Well, the derivative of tangent is secant squared. So we're going to multiply this by secant squared of the inner function, which is 3x to the fourth plus x squared. And then we multiply that by the derivative of the inner part of the tangent function, 3x to the fourth plus x squared. So then derivative of 3x to the fourth plus x squared, that's 12x cubed plus 2x. All right, so now we've applied the chain rule completely. Now, one other thing that we have to be careful about, okay, and this is dead puppy territory here. When you simplify this or when you sort of rewrite it, make sure that you do not inappropriately multiply or combine the factors or the parts of the expression. So, for example, there might be a temptation to try to multiply the 3x to the fourth plus x squared by the 12x cubed plus 2x. No, don't do that. That's a dead puppy right there. And so what you have to do in that case, and the reason for that is because the 3x to the fourth plus x squared is an argument of the secant function. So that's part of the secant function. And so we can't multiply part of the secant function by this, the 12x cubed plus 2x, because that's not part of the secant function. Typically, when this happens, when we kind of write the function in its final form, we tend to write those factors in front so we don't make that mistake. So here we can write this as 2 times 12x cubed plus 2x times tangent of 3x to the fourth plus x squared times secant squared of 3x to the fourth plus x squared. All right, so now the way that the answer is written here is typically sufficient. Now, there are a couple things that you could do. You could perhaps look at factoring the 2x out of 12x cubed plus 2x and putting it with the 2 out in front, or you can multiply the 2 across with the 12x cubed plus 2x to get 24x cubed plus 4x, and then leave everything else as it is. So there are a couple things you could do to kind of tweak it. However, at this point, it's correct, and I think everything's good at this point. One thing you don't want to do, you want to try to simplify when you get these problems, especially ones that have a lot of steps involved. You do want to simplify as much as possible. But be careful that you don't try to overdo things, because oftentimes the more you try to overdo things to try to simplify it more, the more likelihood of making some mistake that's going to kill a puppy somewhere. So be very careful with that. All right. So I hope that these 4 problems give you a pretty good idea and a good sampling of the types of problems you'll be looking at in practice. If you do have any other types of questions, or you want to see me do some other types of problems involving the chain rule, please leave a comment. If you want to smash the like button, feel free to do so with that as well. All right. So this is Glenn with No Dead Puppies signing out, and I hope that you have a great day and keep on working at it.